Okay, just to follow on from what we were looking at on OneNote. So I'm just going to come back to the simulation that I have been looking at earlier on. And I've switched it here now from the energy lab to the vectors lab. Okay, so you can see that really there. But no, can't see that. Okay, so you just take my word for it. It's on the vectors lab instead of the energy lab. Okay. So what we'll do is let me just displace my mass, and so it's down at position 1 right now. That my displacement is now a positive maximum. Just I'll keep it there. Okay. I'll let it go. Play. And we watch it play out. Okay. So again, just when it gets to that equilibrium line, you can see that the velocity is now huge. So the velocity vector is in green, the acceleration vector is in yellow, and the spring force, and James had a question about this earlier, the spring force itself is the one that the spring is exerting on the mass, as opposed to the force of gravity. The force of gravity, of course, is always pointing down in this scenario, but I don't want to include that in what we're trying to understand about subharmonic motion, because this could be oscillating on a horizontal table and that could very easily be happening. Okay, and the same rules would still apply. So as I let it go and it's on slow motion, you can see that the velocity gets really goes to nothing at the two sides, just like we said. Our force becomes maximum, the acceleration becomes maximum at the two sides. Okay, so hopefully that just makes a bit of sense to you all. Pause that there. Okay, so one of the first things that you would see from our OneNote now is the next thing you would see is this slide about the sign. So the acceleration is directly proportional to minus the displacement, the negative of the displacement, which basically means whatever the displacement is doing, the acceleration, a bit like the force, is doing the exact opposite. Okay. Now, as it turns out, this is an important relationship for you to understand at IB level. Okay, you have to understand that the acceleration is proportional to the minus of the negative of the displacement. Okay. Then if we scroll on down, we've got a couple of different graphs going on here, and I'm just going to zoom in on the displacement one first, and you'll see that the displacement from this graph is negative. Okay, so again, that's just based on a frame of reference. It could be to the right, it could be to the left. Obviously, this one is starting down here. Okay, so down. Sorry, just let me move my head. So our equilibrium line would be here. We are starting it from here. So the displacement vector is down here. That, okay. So that's your initial displacement. Over time, this goes up. Then it gets the equilibrium position. Okay. The displacement goes to 0 at B. Then it goes all the way up this way, and it gets to a maximum positive displacement. So this will be positive x up here, and you can see that that is at C. And then, of course, the spring starts to push back down on it, so it comes back down to B again. Okay, so it's oscillating in this kind of simple motion. It goes back down to B again, and the displacement is 0. Okay, so here x is equal to 0. It continues moving, and don't get too caught up on this thing going up or down. It could also be going horizontally as well, in which case you wouldn't have to worry about gravity. And of course, that's why I set those pictures initially on their side, to kind of take that gravitational bit out of it completely, so as you're not thinking about gravity in this at all. So yeah, you're back to B here. Then, of course, it continues on moving. it comes down as far as A, somewhere the displacement is maximum, and so on and so forth. And you can see that the pattern is repeating. So once you get through this much of it, you've done one full cycle or one full wavelength. Now, it doesn't look much like that, but any time you can repeat the pattern like that, then you've done one full wavelength. Okay? So that's what the displacement is doing. So while the displacement was doing that, if we think about what the velocity was doing, when the displacement was down here, we said the velocity was 0. Because that's a moment where it stops for a sec. And now once it leaves here, it goes up. So that makes it a positive velocity. And you can see that that corresponds nicely here. This is a positive velocity going up on our graph. Then it gets up here as far as point B. And point B is here. It's at the equilibrium position, okay? So at this point, it hits maximum velocity, maximum positive velocity. Then comes back down here to a velocity of 0, and that happens at point C, which is at the top, okay? So again, we have that little moment where it stops at the top again. Then you can just kind of see what's happening. Then I think it's going to come back to point B again, where it's going to get another maximum velocity, but this time it's going back down this way, and that would be a negative velocity. Okay, that would be our negative velocity. Again, to get pulled on the spring, turns around and comes back up to here, which corresponds to point A from this graph, which is which is down here. Okay. So again, we get one full repeating pattern in that same time frame. Okay. So between here and here, this is one wavelength. Lambda, of course, being the symbol for wavelength. Okay. If you go through it yourself now and think about the acceleration, well, the acceleration was doing the opposite, the same thing, but in the opposite direction to the displacement. So again, I think the displacement one is probably the best one to think about. Where the displacement was negative maximum, the acceleration was positive maximum. Okay, because when the spring is down here, when the mass is down here, that's got the most force pointing up. Again, following through, point B corresponds to where the acceleration is 0. And the acceleration is 0 when there is no force acting on it, which again is here. And point C goes to the other extreme, where it gets up to the very, very top. The force is maximum now, but it's pushing down this way. The acceleration is now pointing downwards, which we're assuming is going to be negative. So again, you can see that this pattern just keeps continuing on and on and on. And really and truly, there's no difference whatsoever between any of these graphs, except what's called a phase shift. If you could imagine that if I caught the displacement one and moved it back slightly one, okay, moved it back by this much, then you would get this graph, which would be the velocity graph. And if you were to catch the velocity graph and pull that one back by another A to B section, then you would get the acceleration graph. Okay, and it just so happens to turn out, well, we've noticed from kinematics anyway, that if you have a distance time graph or a position time graph, okay, position versus time, if you get the slope, the change in x divided by the change in time, then that will give you the velocity. That's exactly what we get here. If you get the slope of this at any one point, Now, what I've done here, just so as you can kind of have an idea of what this slope thing is about, I've popped in a little link somewhere on this page to do with GeoGebra, okay? And it is, that's here, okay? Drawing derivatives. So a derivative in mathematics is about a slope, okay? So if you are looking for the slope of a line at any one point, then you basically get the derivative of it. I'm not quite sure if you guys have studied it in math yet, but it would have notation that would look like this, dx dt, okay? And it's basically the change in x divided by the change in y, or the change in time, which turns out to be velocity, okay? And if we take the slope of velocity time graph, then we get the change in velocity divided by the change in time. That would give you the acceleration. So the slope of one gives you the other, gives you the slope of the position time graph gives you the velocity time graph. The slope of the velocity time graph gives you the acceleration time graph. Okay? So I know it's a bit of a mouthful to maybe get your head around, but that is what's happening there. I think I'm going to stop this video here because I've been rabbiting on for quite a bit. Please go have a look at that simulation that I posted up here. Put in a sine function. Okay, so if you put in f of x equal to, we'll give it some amplitude, maybe like 4, just as you can see it properly. 4 sine x. Okay, and you'll get a nice sine curve. And then if you, this one, if you turn on the derivative, okay, you'll be able to see that when it comes out, it will look a lot like one of these other graphs. Okay, so give that one a go.